Operations on sets. So dear students, today we are going to discuss about operations on sets, like union of sets, intersection of sets, difference of sets, complement of a set, etc. Okay, so now first union of sets. See, let A and B are two sets, then their union is also a set. It is denoted by A union B. So, if A and B are two sets, their union is denoted by A union B. So like cup. You should be very careful in writing the notations. A union B. A union B is also a set again. A and B are two sets, their union is also a set, and A union B is equal a set of all x such that x belongs to A or x belongs to B. So A union B contains all those elements which contains at least in one of the sets or in both the sets. So, for example, suppose A is equal 1, 2, 3, 4 for a moment, and B is equal 3, 4, 5, 6. Then their union is equal A union B is equal 1, 2, 3, 4 union 3, 4, 5, 6. Then it is nothing but 1, 2, 3, 4, 5, 6. So in union, you have to collect such elements which are present either in A or in B or in both. That comes in union. This is about union. Coming to intersection, if A and B are two sets, then their intersection is denoted by A intersection B. It's like cap, A intersection B. And it is defined as a set of all x such that x belongs to A. Here you get and x belongs to B. Suppose if we see with an example, A is equal 1, 2, 3, 4 and B is equal 3, 4, 5, 6. Then A intersection B, suppose if you want to find A intersection B is equal 1, 2, 3, 4, intersection 3, 4, 5, 6. Now, intersection means such element will come in intersection which present in both the sets, which elements are present, those elements you have to collect. That means common elements. So here, what are the elements you are seeing in both the sets? See, 3 and 4 you are seeing in A and as well as in B. So only 3 and 4 are the elements which you are seeing in common to both the sets. So it comes in intersection. This is A intersection B. So union of sets over intersection of sets over union of sets over intersection of sets over. Now difference of sets. Say A and B are two sets, then if you collect all the elements which exclusively belongs to A, that is called A minus B, and if you collect all those elements which are exclusively belongs to B, those are called B minus A. That set is called B minus A. For example, first let us write the definition. A and B are two sets. Then A minus B, set of all x belongs to A such that, set of all x such that x belongs to A and x does not belong to B. So now we are discussing difference of sets. Let A and B are two sets, then A minus B is equal a set of all x such that x belongs to A and x does not belong to B. That means the exclusive elements of A. So you have to collect the elements of only A. That means those elements which are in common you have to ignore and you have to collect only the elements of A. It is called A minus B. So B minus A means set of all x such that x does not belong to A and x belong to B. So you have to collect the exclusive elements of B. So you have to collect the elements which present only in B. The common elements you have to ignore and you have to collect the elements of only B. That is called B minus A. Now let us take an example. A is equal A, B, C, D, E and B is equal A, B, G, H, F. Say for a moment. So these are two sets A and B. So now you have to find A minus B and B minus A. So A minus B is equal to, what is A? A, B, C, D, E minus, what is B? A, B, G, H, F. So now you have to collect the exclusive elements of A. So you have to ignore the common elements and you have to collect only the elements of F. So first you see what are the common elements here and here. So you are seeing A and B are the common elements in both the sets. So now ignore A and B and collect the only elements of A, C, D, E, that is called A minus B. Now let us go for B minus A. So B is A, B, G, H, F minus A is A, B, C, D, E. Now ignore the common elements that are A and B and you collect only the elements of B, which are G, H, F. So this implies G, H, F. This is B minus A. So we can easily observe that A minus B is not equal to B minus A. It is an important note. Did you understand? So now coming to complement of a set. See, before going to complement of set, I have to give a small definition, which is universal set, which plays major role in mathematics, especially in sets. Universal set. Universal set means, as far as a problem is concerned, whatever the sets are under discussion, those all sets will be subsets to a particular set. Then that particular set is called universal set. So, did you understand? So, universal contains all the sets in the discussion. In the discussion, whatever the sets are there, those all sets are subsets of the universal set. Say, I will explain with an example. Before that, I will give symbol for universal set. So the symbol for universal set is mu. Universal set is denoted by mu. Now, I will explain taking an example. Suppose, say, in a problem, the following sets are under discussion. Say A is equal to A, B, C, D. Say B is equal to A, E, I, O, U. Say C is equal to X, Y, Z. Say D is equal to P, Q, R, S, T. Say E is equal I, J, K, L. Say F is equal to M, N, O, P. So like this, say, for example only this is. So in a problem, say, these all sets are under discussion. So as far as this problem is concerned, what will be the universal set? It is set of all English alphabets, because universal set contains all the sets which are under discussion. Means all the sets which are under discussion will be the subsets of the universal set. So here, as far as this problem is concerned, the universal set is equal to mu is equal to the set of all English alphabets A to Z. Because here now you can see A is subset of mu, B is subset of mu, let's say all sets are subsets of mu in that particular question. Did you understand? This is the universal set. Now what is complement of a set? See, Let mu be the universal set and A be the given set. Obviously, A is a subset of mu. Obviously, A is subset of mu. Now, the complement of set A is denoted by A complement. It is read as A complement. And is defined as A complement is equal mu minus A. Means exclusively the elements of mu. So you have to ignore the common elements of A and mu, and then you have to pick up the elements exclusively in mu, not in common. So it is called mu minus A, which is A complement. Now let us take an example. Suppose if you go for example, say mu is equal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And suppose A is equal 4, 7, 9, 10. Say for a moment. This is A. Obviously, A is subset of mu by definition itself. Now find A complement. So, as per the definition of A complement, so A complement is equal mu minus A. So what is mu 1 to 10? What is A? 4, 7, 9, 10. So what are the common elements? 4, 7, 9, 10. So you ignore 4, 7, 9, 10 from mu and you pick up all the remaining elements, which are 1, 2, 3, 5, 6, 8. Right? So this is called A complement. Exclusively the elements of mu. Understood? Not A. Exclusively the elements of mu. This is called A complement. Now, one famous principle we have, A complement, whole complement is equal to A. It is also called A double complement. A double complement is equal to A. Understood? Right. Now, I am going to define what is ordered pair. This is also important in algebra, ordered pair. In geometry also we use ordered pair in coordinate geometry. So everyone should know what is ordered pair. See, I will explain. See, there is a set A with some elements in it. There is another set B with some elements in it. Now, if you collect one element from set A and one element from set B, and if you make an arrangement of those two things in an order, then it is called ordered pair. First, order we are putting in order, okay, and we are putting in order two elements. Two elements are arranged in order, simply saying. Two elements are arranged in order. So that is why it is called ordered pair. Pair means two. Those two elements will come from two different sets or from same set. Sometimes from same set also we can pick up. But come what it may be, whether they are different sets or they are same sets, no matter, but those elements are to be taken from two sets, equal or different. See, for example, A is equal to 1, 2, 3. So B is equal to some 4, 5, you say for a moment. Now, if you pick up some ordered pairs, so you take an element from set A, one element from set B, and you put them in order. So this is an ordered pair. Similarly, 2, 4 is an ordered pair, like that, etc. All are ordered pairs. Not necessary to be taken from the first element from set A, the second element from set B. You can even take the first element from set B and second element from set A. Those are also ordered pairs. 4, 1, 5, 2, these are also ordered pairs. So, no matter from which set the element is picked up, but if you pick up one element from one set and another element from another set, and this ordered arrangement is called an ordered pair. Now, just I defined what is ordered pair. Now I am giving some important properties of ordered pair. The most important thing is ordered pair AB is different from ordered pair BA. Though both are the ordered pairs, they are different because the order has been changed. The moment you have changed the ordered pair is considered to be changed. So, ordered pair AB is different from ordered pair BA. And the second important property of ordered pair is, if ordered pair AB is equal to ordered pair PQ, if and only if A is equal to P and B is equal to Q. This gives us the equality of two ordered pairs, the information about the equality of two ordered pairs, when the two ordered pairs are equal. Ordered pair AB is equal ordered pair PQ if and only if A is equal to P and B is equal to Q. Coming to next property, ordered pair AA means it is not simply A. Don't mistake like that. Ordered pair AA means ordered pair AA only. It is not simply A. So these are the most important things. So now we have discussed union of sets, intersection of sets, difference of set, complement of set. Now we have one more operation, that is cross product of two sets. This is also called as Cartesian product of two sets. So now Cartesian product of two sets. See here, let A and B be two non-empty sets. Let A comma B be two non-empty sets. Means none of the A and B is empty. Then their Cartesian product or simply cross product from A to B is denoted by A cross B. And it is defined as A cross B is equal to set of all ordered pairs x comma y such that x belongs to A and y belongs to B. So let A and B be two non-empty sets, then their cross product from A to B is denoted by A cross B and is defined as A cross B is equal to set of all ordered pairs xy, where x is taken from set A and y is taken from set B. Now cross product from B to A is defined as B cross A is equal to set of all ordered pairs xy such that this x is from B now and y is from A. Now the first element is taken from set B, the second element is taken from set A. The most important thing is A cross B is not equal to B cross A. A cross B and B cross A are different. So you please understand this. When A and B are two non-empty sets, then their cross product from A to B is denoted by A cross B. And in A cross B, you will see the collection of all ordered pairs in which the first element is taken from set A and the second element is taken from set B. Whereas in B cross A is also set of all ordered pairs. Ordered pairs are the elements in B cross A. Even in A cross B or in B cross A, ordered pairs are the elements. It is very clear. Now in B cross A, in every ordered pair, the first element is taken from set B and the second element is taken from set A. And finally, A cross B is not equal to B cross A. They are different. You please understand this. Now, let us see an example. If you go for an example, suppose A is equal 1, 2, 3 and say B is equal to 4, 5. Now A cross B and B cross A, let us find out. A cross B is equal 1, 2, 3 cross 4, 5. So what are the elements you get? All ordered pairs in which the first elements are taken from A and the second elements are taken from B. So now let us pick up all such ordered pairs. 1, 4, 1, 5. 2, 4, 2, 5. 3, 4, 3, 5. This is A cross B. Now go for B cross A. So 4, 5 cross 1, 2, 3. So this is a set of all ordered pairs in which the first element will come from B and the second element will come from A. So this is 4, 1, 4, 2, 4, 3, 5, 1, 5, 2, 5, 3. Now you can see easily that A cross B is not equal to B cross A. Understood? Now next we will discuss what is relation. After relation, the function will come into the picture. Okay? Now relation. The definition is any non-empty subset of A cross B is known as a relation from A to B. Any non-empty subset of A cross B is known as a relation from A to B. See, in the previous example, we have taken A cross B. Just I am taking the previous example only. So, in the previous example, what A cross B we got as 1, 4, 1, 5, 2, 4, 2, 5, right? 3, 4, 3, 5. This is A cross B we got. Now you take any non-empty subset of A cross B. Any non-empty subset of A cross B you take. It means you have to take a subset of A cross B which is not empty. So, how many elements you take? No matter. Only the condition is it should not be empty. So, you can start with one element, two element. So, your wish, that is. So, here I am collecting some subsets of A cross B as my wish. So, this is one subset. This is another subset. So, another subset of A cross B. So, etc. These all are subsets of A cross B. So, these all are relations from A to B. Subset of A cross B will be a relation from A to B. Now, you can take a note. A non-empty subset of B cross A is said to be a relation from B to A. See that this from where to where, this order is important. So, a non-empty subset of B cross A is known as a relation from B to A. So, whether it may be a relation from A to B or it may be a relation from B to A, you will see ordered pairs in a relation. So, relation is set of ordered pairs. So, in any set, if you are seeing ordered pairs as elements, then it is a relation. Once again I will repeat, in any set, if you are seeing ordered pairs as elements, then that set is a relation. So, a relation, if you want to define in a simple language, a relation is set of ordered pairs. So, if you define relation in a simple way, a relation is set of ordered pairs. Right. So now relation is over. So now the next important concept is function. Hereafter the main topic begins, functions. So now function. See, a relation from A to B, in order to set to be a function from A to B, it should hold some conditions. In a relation, if those conditions are satisfied, then that relation will be a function. So here one thing one should understand, after all, function is also a relation. So all functions are relations, but all relations may not be functions. See, this is most important thing that everyone should understand. A function is a relation, but a relation need not be a function. So a relation coupled with some specific properties is said to be a function. A function finally is a relation. Understood? So, what are those conditions that a relation should follow in order to be a function? Here I will discuss. So, first let us write a relation from A to B is said to be a function from A to B if and only if, number one, whenever there is an element A member of set A, it should imply that f of A should be a member of B. So this is most important, and this should happen with respect to all elements of A, for all A belongs to A. So whenever there is an element A, for such an element A, okay, an element f of A should be associated in B. That too in B, because here we are talking about a relation from A to B. A to B is said to be a function from A to B. What should happen? Whenever you are seeing an element A belongs to A, that particular A should have an association which is denoted by f of A. Hereafter it is called image of A, and it should be in B. It should be in B, and this should happen for all A belongs to A. For every A belongs to A, the corresponding image should go in B. Suppose in any circumstance in set A, if any element is left over without being associated with an element of B, then this first condition is failed. The moment any condition is failed, it remains a relation, but it cannot be a function. Understood? See the diagram, if you see diagram, the diagram will come like this. Whenever there is A, there should be an image f of A in B under F. This should happen. You should see, every student should see this. Secondly, no two different elements should be associated with the same element in B. This second point is, for single element of A, there should not be two associations. This is correct. The second statement which I have given is correct. So, for single element of A, there should not be two different images. How you mathematically express this? See this second point. Whenever A1 and A2 are equal in A, then the corresponding images f of A1 and f of A2 which are in B, those also should coincide. The identical elements of A should have identical images in B. On contrary, if you go, what is the opposite statement for this? A1 is equal to A2. I am saying on contrary. This is just opposite I am saying. Contrary means opposite. So if you understand opposite, you can understand this more clearly. So what is its opposite, negation? You need not write this in the examination, only for understanding purpose I am writing. What is the negation of this statement? A1 and A2 are equal in A, and f of A1 and f of A2 are different in B. It's contrary to this statement. Contrary means opposite, quite opposite. The quite opposite statement of this second point is A1 and A2 are equal in A, and f of A1 and f of A2 are unequal in B. Understood? If this happens, it cannot be a function. So these two conditions should be obeyed, a relation to be a function. Now here I will give some examples. Let us take various examples for various relations, and from them let us pick up the relations which are functions, so that you can understand more clearly whatever we have discussed here. So now here you see I am taking arrow diagrams for various relations from A to B, where A is equal, say for a moment, 1, 2, 3, B is equal 4, 5, 6, 7. Only for example I am taking this. Say A, B, arrow diagrams I am taking 1, 2, 3, 4, 5, 6, 7. Now I am taking some random relations from A to B. Say some F1. F1 is a relation from A to B here. Now whether it is function or not, we have to decide. First let us see the first condition, whether all the elements, each and every element of A is having some or other association in B. Means is it connecting with any of the element of B. See here, 1 is connected to 4, 1 is connected to 5, 2 is connected to 6, 3 is connected to 6. So here each and every element is having some or other association in B. So clearly that first condition is justified here. Now let us see the second condition. What is second condition? Whenever the elements are equal in A, their corresponding images should be equal in B. That means what should not happen? What should not happen? Single element of A having two images. Single element of A having two images. It is opposite to the second condition. This should not happen. Now here you see the single element of A having two images. Single element of A, which is 1, having two different images. Like one person having two PAN cards. One person having two voter IDs. This is not even acceptable in society. You see, in any place in India, can one person have two PAN cards? No. It's a crime. In society it is crime, in mathematics also it is crime. One element should not have two different images. One element of A should not have two different images. So it is a relation, but it is not a function. Understood? Now let us take another example. So here F2 is another relation from A to B. Is it a function from A to B? No. Because here the element 3 in set A has no association in set B. It is left over without any image. That should not happen. So it is a relation, but it cannot be a function, as 3 has no image in B. So not a function. See, F3 is a function because the two conditions have been satisfied. Every element of A is having some or other image in B, and secondly, single element of A, you see any single element of A having two different images? No. But two elements can have one image. One element cannot have two images. Please try to understand, don't get confused. Single element should not have two different images. But two different elements of A can have single image. Like, for example, see, take me. My name is Raghuram. So legally I should have only one name, and I should not have another name. Say for example, Peter. See, Raghuram cannot be Peter. So this physical body should have only one name. This physical body should not have two names, Raghuram and Peter. See, that is it. So one person should not have two names. Similarly, one element of A should not have two different images. But see, I am Raghuram. On the way, there is a person whose name also is Raghuram. Can happen. So two different persons can have one name. See, understood? Two different persons can have one name. Like two different elements can have same image, but one element should not have two different images. Understood? So this is the functional concept. So now you understood the difference between relation and function, right? Once again, I am repeating. All functions are relations only, but all relations are not functions. So coming to the next point, some important points that you have to take, that is first and foremost, notation. When a relation A to B is a function from A to B, then it has a specific notation. That notation I will introduce now. A relation F from A to B is said to be a function, a relation F from A to B is if a function from A to B then it is given by the notation a relation F from A to B is if a function from A to B is if a function from A to B, then that is given by the notation, and this notation, and it is read as F maps A into B. F maps A into B. So this is how you have to read, F maps A into B. And this notation you have to use only if F is a function from A to B. Just it is a relation, you should not use this notation. You are using this notation means it is a function from A to B. Understood? So now here I am giving you some important points. When F maps A to B, okay, you can see some important concepts. Number one, in such case F is said to be well defined. So when F is a function from A to B, then we can say that F is well defined. Second, the set A is said to be domain of F and set B is said to be codomain of F. Codomain. So when F maps A to B, A is said to be domain, B is said to be codomain. And coming to next important is range. When F maps A to B, the range of the function F is denoted by F of A. And this range is equal to the set of all F of A such that A belongs to A for all A. So when F maps A to B, the range of the function F is denoted by F of A, and it is defined as F of A is equal to set of all F of A such that A belongs to A for all A. So it means that you have to collect all images of the domain elements. For all domain elements, you have to pick up the images, and all images are to be taken in a set. Then that set is said to be range. So the set F of A is equal to this is known as range of the function F. And obviously that range is always subset of codomain, because after all images you are collecting, images are the codomain elements only, no? Images fell in codomain only. So after all you are collecting all images of domain elements, so obviously the set of all images is a subset of B. So range is a subset of B. So now let us take an example. Let us write there what is domain, what is codomain and range, and let us see that this concept also, range is subset of B there. So if you practically see one example, you can understand more clearly. See, for example, suppose let us take an arrow diagram. Just example only. So here I am taking a function f from a to b. It's a function. Now let us write domain, codomain and range. So here f maps a to b, obviously, because the two conditions are satisfied, you can see. So the domain is 1, 2, 3, 4, 5. The codomain is it is nothing but set B. Codomain I am writing here. So codomain B is equal 6, 7, 8, 9, 10, 11. Now let us write range. Range is denoted by f of a, means it is the collection of all images of domain elements. So what are the images? You are seeing just images 6, 7, 8 and 9. These are the images of the domain elements. So here you are seeing clearly that range is subset of B. So in functions, this most important point is range is always subset of B. Please do understand. So what is our next topic is types of functions. Okay, we'll discuss.